All right, so obviously I'm not here today. We're going to do a couple activities. It won't be too hard. So you can see the plan for today is electronegativity. And then we're going to color your periodic table. And we'll use the half-side periodic table for that and some colored pencils over in the lab. And then we're going to draw a graph and talk just a little bit about that. And it really should be a pretty simple day. Hopefully you can get through all of it. So the first thing we're going to talk about is the idea of electronegativity. And if you've had Mr. Burt, he calls this the hotness factor of an atom, and that works just fine. Electronegativity is the power of an atom to attract electrons to itself when it is bonded to another atom. All right, you may recall, and I dang well actually hope you do, that I've been saying the metals are losers because they lose electrons. All right, and then these nonmetals, they gain electrons because of their configurations. They're closer to the octet. Metals, to lose, they get closer to the octet. But we have losers and we have gainers. All right, electronegativity will follow kind of the same idea. If electronegativity is the power of an atom to attract electrons to itself, then that would be the things that would gain. Losers of electrons will not have very high electronegativities, and they cannot attract electrons to themselves in atoms. In fact, they don't want electrons. They lost them in the compound. That made them happy. They are happy to lose. The nonmetals, they gain, they want, they steal, they do everything they can to have that electron. So based on losing and gaining, we could also then say that on the periodic table, over here we have high electronegativities, and over here we have low electronegativities. Now, electronegativity difference between the two atoms, which we're going to graph in a little while, will explain why we have different types of compounds. We're going to learn about ionic compounds, polar covalent compounds, nonpolar covalent compounds. Those all come from this idea of electronegativity. And it's the idea, going way back to the slide we said on the octet rule, that atoms will lose, gain, or share electrons in order to become a full octet, like a noble gas. Electronegativity and the power that the atom has to attract an electron to it will determine whether it loses, whether it gains, or whether they have to share. For example, if we look right here, and remember, none of this, whenever we talk about this stuff, nothing ever really counts 8, because they're the noble gases. So we're talking about here. Fluorine is that top left or top right corner. Fluorine then would have a very high electronegativity. If fluorine came in contact with a metal, like something, we'll just do Na, all right, this has a very low electronegativity. So when these two are by each other, sodium will lose, because it's a metal or a loser, it will lose its lone valence electron to fluorine that has 7. It comes and parks itself right there. Since sodium is very low and fluorine is very high in electronegativity, these do not share. This one is a loser. This one gains. We will call these things ionic bonds, because when you lose an electron, you become a positively charged ion. When you gain, you become a negatively charged ion. So the type of bond, ionic, is all determined by the difference in electronegativity in the two atoms. And we'll do a lot of that when I get back, but for now, hopefully that's a decent understanding of electronegativity. It's the ability of an atom to attract electrons to it. Metals have low electronegativities. Nonmetals have very high electronegativities. All right, now you're going to do this activity on your periodic table. And it's your half periodic table. So you probably don't see this very well. But it's the one that has the transition metals cut out of it. So if you will take that out and then look at these directions, you will see that you're going to do the following. You're going to color the elements with the lowest electronegativity, 0.7, purple. Now, one second. When you look at these elements, you'll have hydrogen, and it'll have a 1 and a 2.1 in the corner. I got to come back to me, I guess. So when we do this, these numbers in the bottom right-hand corners of the atoms, these are the electronegativity values for each one of these atoms. So when it says find these that are 0.7, we're looking in the bottom right-hand corner to see which ones are 0.7. All right, so you have these rules in your lab book. You have them here. Go ahead and grab some colored pencils and get started. If you'll look real quick, I don't have all of these colors enough for all of you to have that exact set of colors. So you can grab whatever pencil color you want. Just make sure you color the groups the same colors as they are listed here. This will take 5 to 10 minutes, so the substitute will pause the video and you go ahead and do that activity. All right, this will not let me shrink this down so you can see it on all on one slide. And let me move this right over here, get that out of the way. But hopefully, there's some things on here that are a little weird, but hopefully your coloring system looks pretty much the same as this. If I scroll down, you'll notice here, just check yours real quick that you have the same groups colored. And then once you do, I would like you to look just back into your lab book, and you will notice that there are a few questions. Let me get those questions up here. All right, so based on that graph now that you just had, will you take a moment and answer these 4 questions? You won't know, I guess, the bottom 2. I'm sorry. So just do these top 2. Within a family, so that means up and down, what is happening? And within a period, that means side to side, what is happening on electronegativity. Do it yourself, then just check with your lab partner, make sure you're good, and we'll just pause this for a good 30 seconds. All right, so within a family, electronegativity generally does what as atomic number increases? So as we go down, that's what atomic number increases means. The electronegativity generally decreases. Within a period, generally we do what? We're moving from family 1. So as we go that direction to the right, it generally increases. So based on that, it just goes on what we said. The higher and righter we are, the more electronegative. Now, the greater the difference is the blank here. In electronegativity, the greater the strength of the bond between the 2 atoms. And the strength is measured in the amount of energy needed to break whatever. That's the wrong one, but I'm a driver's ed teacher, so who cares? The energy needed to break the bond. So now we should have that colored, and now time for our next activity, which is just on the next page. All right, so the next activity we're going to do, and if this doesn't flow perfect, I apologize. This recording is 4 hours later than the first part of this recording. The next thing we're going to do is graph the information on this next page. So what this graph is going to do, it's going to graph electronegativity difference to percent ionic character. And that might not make sense at first, but we will try to make sure it makes sense as we go along. So what you're going to do, the instructions say graph the above data, label the y-axis percent ionic character, which is what I've already done. So there's your y-axis label, and your x-axis label is electronegativity difference. And anytime the sub needs to pause this so you can do this, go ahead and ask her to pause it. All right. So what you need to do is you need to label your axes now so that these numbers will fit. And I've done this for years, and kids don't really like it because if you go by 5s, you run out of space. If you go by 10s, it's too small. But whatever. Choose something here and go ahead and have the substitute pause it, or if you're watching at home, pause it. And label something for your electronegativity difference between 0, because your lowest one will be 0.2 and your highest is 3.2. 3.2 right here. And then whatever, just label whatever you want. If it's 0.2s, 0.4s, 0.6s, or whatever, I don't really care. And I'm not going to be real accurate on mine. And then on the side here, you have your percent ionic character, and it goes pretty much from 0 to 92. So 0, and then I'm going to put 100 up here. And then, I don't know, if you go by whatever, I'm just going to say 20, 40, 60, 80. And I know those aren't equal, but whatever. So once you have that labeled, then you make the graph with these as your data points. So for this row, the difference is 0.2. So let's say that's like right here. And the percent ionic character is 1. So that would just be right about right there. And then you go down 0.4 and it's 4. And then 0.6 and it's 9. Okay, and it's not linear, I promise. It just kind of looks linear. Eventually you'll get some dots like this or something, and it won't really look like this, but let's say it looked like that. Then just connect them if you would. So plot these data points, have the substitute pause it, and fill those in. All right, now that you're done, hopefully, we're going to do some other parts. It says mark the divisions between the bond types and label each section or something like that. So what we'll do is I'm taking these lines that are right here and I drew them vertical right here. So if you'll notice, this line is right around 1.7. So this would be that was the second one. So I'm just going to put 1.7 here and have that line. And the other line is at 0.5-ish, 0.6. The notes, I think it says it's 0.6. So put a line right there. So put those vertical lines, and then it says to label these 3 sections. So this first section is your non-polar covalent. You can write the whole thing out. The next one is polar covalent, and this is ionic. So go ahead and add that to your graph. All right. Now we're going to take the periodic table that we just used and combine it with this graph to figure out the type of bonds when 2 atoms combine. It's pretty simple. We simply need to find their electronegativity difference, put it where it goes on this graph, and then we're ready to roll. So let me come back to the graph. All right, and I'm going to clear a lot of this out. In fact, pretty much everything. So the way this works is you'll be given a formula, like just table salt. Its formula is NaCl. And what you do is you find Na, and you find Cl, and you find their electronegativities. Right now, chlorine is a 3, and sodium is a 0.9. So to determine the bond type, you find the difference between these. And whenever we find the difference between 2 numbers, we subtract the small from the big. So it's 3 minus 0.9, and that will give you 2.1. Now that number doesn't mean anything. I don't know what just happened. It keeps doing that. That number doesn't mean something specific, but it's the number we're going to use on this graph. So we'll put a big blue dot at 2.1, and let's say it's like right here. Well, that was a stupid place to put it on the work, but you can see that is in the region that would make an NaCl type of bond ionic. All right, just a couple of things. If we do this for water, water has the formula of H2O. In this activity, we do not worry about that subscript. Now, it's important in chemistry, but it's not important for this activity. So we still simply find the difference between H's and the difference between O's. So we have 2.1 for hydrogen, 3.5. So we take the big one and then subtract the small one from it. This is 1.4. We go to our graph. Oops, I went the wrong way. I'm sorry. One too far. And the difference was 1.4, which would be in here somewhere. Probably, I guess, closer here, but whatever. So water is a polar covalent molecule. So you've always heard water's polar. Now you know why water is polar. It's because the electronegativity is greater than 6, but less than 1.7. Now what I want you to do is practice it by doing these next examples. All right, so use your graph and use your periodic table to determine the type of chemical bonds involved in these 6 things. Now, the substitute you have right now is pretty smart and knows that one of these will give you a math answer, but she probably knows one of them also is not what the math answer tells you. Currently, just go with what the math tells you, and we should be fine. So, anyway, we'll wrap that up. There are some questions in the homework that you can do with this information. Hopefully this wasn't too hard, and we should be just fine. See you guys on Monday.